Hi, I'm Célian Boyé, PhD student in the EP team of the Aerospace Department of the UC3M. As I am currently in an international exchange in the electrical propulsion team of the CNRS of Orla in France, I'm presenting here my progress upon the design and development of a magnetic arch cluster. My thesis is supervised by Mario Merino and Jaume Navarro, and the international exchange is supervised by Stéphane Mazoufre. This thesis is executed through the Doctoral project funded by the European Research Committee. The presentation will be divided into 6 main sections. First, the motivation behind the Disaster project, past activities realized throughout the 3 previous years of my thesis, and the evolution from the previous prototype to the third one. Then we focus on the preliminary test campaign I made in Madrid's laboratory in December, the current international exchange I'm currently performing, and then the conclusions on this last year of thesis. The Doctoral project aims to revolutionize the space propulsion field by developing some new electric propulsion devices based on magnetic arch thrusters and clusters, on which I'll be coming back later. The EP devices designed throughout this thesis rely on the ECL principle to generate plasma and thrust. In a magnetic field, electrons have a circular motion due to the Lorentz force. When this motion is overlaid by an axial motion, it transforms into a cyclotron one defined by the strength of the applied magnetic field. Plasma generation is then enabled by collisions between electrons and neutrals. The sources used for the second and the third prototypes rely on the design shown in the scheme. As you can see, these devices consist of 3 main parts: the power injection, with coaxial cables in our case, coils or permanent magnets to generate the magnetic field, and gas injection. During the past years, I've designed, procured, assembled, and tested both a first prototype consisting of a U-shaped thruster and a second based on the 2 ECR sources with opposed polarities. Test campaigns have been realized for both, and they both have been a world premiere. One conclusion we drew from the second prototype was that the magnetic topology does not prevent plasma extraction. Moreover, I participated in both the Plasmatech 2023 in Lisbon and the UCAS CES 2023 in Lausanne, during which I presented the results from the second prototype. A journal article has been submitted and is currently in review following these conference papers. From the experience of the 2 first prototypes, I've developed in September a third version of the magnetic arch cluster. The main improvement consists in the groove-type injection in the ionization chamber in order to distribute the gas in the best possible way before it gets ionized. Moreover, a pre-chamber has been placed to avoid asymmetries due to one-point gas injection as in the second prototype. The copper core is responsible for generating the sufficient magnetic field, allowing the ECR phenomena have been replaced by N42 permanent magnets to extend drastically the operation time of the thruster, as the core is rotating too much. And finally, a single plate is now in use to ease the alignment of the sources during assembly. Preliminary to the research stay I'm currently doing in Orléans, I've completed a test campaign in UC3M propulsion laboratory to determine the plasma characteristic with electrostatic probes for different operation points in terms of mass flow rate and microwave power. This has been used as a propellant with mass flow rates going from 0.2 mg per second to 2 mg per second, whilst microwaves are with a frequency of 2.45 GHz and a flow power in between 50 watts and 200 watts. Simulation of the magnetic field have been performed in order to determine the important magnetic field lines, such as the one starting from the ionization chamber in gray, or the antenna site in purple, or even the center line of the antenna in pink. Moreover, the magnetic field have been probed to confront with simulation data at different heights on a 2D horizontal plane. Symmetry in between the sources have been improved experimentally, and differences between simulations and experimental data have been found negligible. I will quickly on these results obtained during the preliminary test campaign. The Faraday curve measurements helped us to determine 3 different types of profiles in terms of ion flux depending on the mass flow rates, such as the Gaussian type distribution for 2 CCM, 2 peaks aligned with magnetic field lines coming from the antenna for 5 CCM, as you can see on the right of the screen, and a middle peak resulting of the merging of 2 of the plasma beams for 10 CCM, as you can see on the left part. Small symmetries can still be found in terms of ion flux between the sources, regardless of the operation points. The ion most probable energy has been determined thanks to the retarding potential analyzer at angles of interest, like peaks, drops, or plateau. These points of interest have been found thanks to Faraday curve measurements of the ion flux. Finally, Langmuir probe measurements have been performed on a straight line on the cluster symmetry plane from 50 mm to 300 mm from the cluster exhaust plane. Putting the probe closer to the thruster would have been too intrusive to get accurate results, indicating both that the merging beam seems to be closer than 100 mm, as we can see an increase in temperature and density at 50 mm, and that some non-intrusive measurement methods need to be used to determine plasma properties in the merging beam. Laser-induced fluorescence is one of the non-intrusive measurement methods that we can use. This spectroscopy method allows to measure, among other properties, the velocity of the studied species. In our case, it's the xenon ion. It relies on the excitation from one quantum level to another of higher energy by absorption of a photon of energy matching the difference between two levels. The isotropic fluorescence occurs when a probed ion, excited by the laser, de-excites to a lower energy state and emits a photon. As selection rules bound the energies allowed from the previous stated optical transitions, a specific species can be analyzed. The end velocity can then be determined thanks to the Doppler effect caused by the absorption frequency to be shifted when the studied species is moving. The scheme shown is actually not fully representative of the current setup, as some elements have been moved and some are not in use, but it carries a general idea of the optical bench I'm using. A laser beam is generated, then split. Half goes to be analyzed with a photodiode and a lambda emitter, just to get the power and the wavelength of the laser, and half is injected into the vacuum chamber thanks to an optical fiber, and then it's aimed toward the cluster or to other points of interest. An optical detection branch, also linked to an optical branch, is linked to a photomultiplier that determines the intensity of the probed signal. A sweep in the laser frequency results in generation of the velocity distribution function. So the higher the density of the particles emitted at a specific wavelength, the more intense the fluorescent signal. The goal of the study is not simply to perform classic LIF measurements, but to get a 2D map of the 2D velocity vector for one side of the cluster, with a few points on the other side of the symmetry plane just to check symmetry. Many measurements have been done, and I present only a quick summary of them. Here you can see a grid of points we are probing, which evolve through the results we are obtaining. So first of all, the actual ion velocity have been determined at the right source exhaust plane. The presence of double peaks are coherent with the Zeeman broadening and splitting effects caused by the high-intensity magnetic field inside the source, as it can be noticed from 12 millimeters away from the antenna, where we have both a peak around 12 kilometers per second and one at 17. More or less, the velocity stays in the range of 15 to 20 kilometers per second in the exhaust plane of the source. The axial ion velocity have been probed along the cluster's symmetry plane. The variation in the axial ion velocity in between 30 mm and 50 mm from the cluster plane matches with the magnetic field lines connecting the antennas, with a drop from 16 km per second to 14 km per second before a constant increase. Thus, we can already conclude that the merging of two plasma beams has an effect on the axial ion velocity. Measurements have been also done on both sides of the symmetry plane in order to check symmetry in between the sources. Apart from a wider distribution function on the left part of the symmetry plane, 30 mm away from the exhaust plane, as you can see on this map, the symmetry seems to be confirmed. Right now, I'm currently working on the data analysis for the 2D map of the ion axial velocity, as we are now probing the ion radial velocity. These combined results will give us a better idea of the ion velocity mapping on the horizontal plane for a cluster of two ECR sources. The third prototype has been designed, procured, assembled, and tested from last September on. It is the second dual ECR cluster to be ignited, and the first to be analyzed via 2D LIF measurements on 2D map. So this exchange is not finished yet, and in the upcoming weeks, with the full 2D grid of the 2D velocity vector will be achieved. However, a more accurate test campaign remains to be done on the first prototype of the magnetic arch thruster in order to determine the viability of the U-shaped thruster. So this is the achievements I've done during last year, such as the participation on two conferences of Plasmatech and UCAS. Also, we have been accepted to participate in the IPC 2024 in Toulouse in France in June to present the results of the LIF. And we have an article in processing with Mario Merino and Joey Navarro about the second prototype results. Thank you all for your attention and for attending to my presentation.